Okay, so we are going to have around 15 minutes presentation and around 5 minutes for Q&A, right?
So shall I start? Hello, can you hear me?
Yes, yes. Okay.
So hi everyone. So today we will be presenting for the diabetes data set. So that's 4 of us in our group. For the first part, so the results from the previous assignment based on the analysis done using the unsupervised machine learning methods, which are we use principal component analysis and the chi-square results for the symptoms in association with diabetes. The variables that greatly affect whether someone is diagnosed with diabetes or not are, as you can see, there are 6 of them: polyuria, polydipsia, sudden weight loss, partial paresis, age, and lastly gender. Okay, and then moving on to the methodology. First, we designed the decision tree. The ratio of training and testing set is 7:3. It is being fitted with all variables, and then we calculated, we estimate with equal prior and estimated prior. And then we do a trial and error for the pruning levels, which is 0.5, 1.5, 2.5, 3.5, and 4.5. This is to see which model we will provide the best result. Our decision is based on the accuracy and precision of the models that we have gotten. And then the formation for the decision tree using 6 selected variables. Actually, we formulate the models with all variables, and the other one we use 6 selected variables as mentioned before. The design of the decision tree for the 6 selected variables mentioned before will be the same as the decision tree with using all variables, which we have 17 variables actually. Okay, and then we compare the models based on the following, which is the split variables, important variables, accuracy and precision, and also sensitivity and specification. Next, I will pass to my group mate.
Hello all, these are our results. So as explained by Farhana before, we're using equal prior and estimated prior, and also the pruning level for 0.5 to 4.5. So when we compare equal prior and estimated prior, we can see the accuracy level is almost same or only slight different, but the precision level is far better in the equal prior compared to the estimated prior. So we are choosing our model only using the equal prior. So among the models with the equal prior, the model with pruning level 2.5, 3.5, and 4.5 are with relatively lower accuracy. Hence, they are excluded from the selection. So the best model that we select is with pruning level 1.5 instead of 0.5 to avoid complex and overfitting model. So our selection is with pruning level 1.5. Next. Next slide. Okay, so after the selection with the pruning level 1.5, these are the model that we got. So we can see here around 7 variables out of 16 variables. First is polyuria, so it's based on the polyuria, and then polydipsia, itching, and delayed healing. And then the other side of the polyuria is gender, alopecia, polydipsia, and also muscle sickness. So from here, we can see that the important variables are polyuria, polydipsia, and gender because of the higher number of end nodes. Next. Then we also used 6 variables from the result of our previous assignment. So when we check here, this model uses all the 6 variables, which is polyuria, polydipsia, age, gender, sudden weight loss, and partial paresis. So among these, we can see the important one is still polyuria, and then polydipsia, age, besides gender, sudden weight loss, and partial paresis. So from here, the most important 3 variable is same as the previous one, which is polyuria, polydipsia, and gender because of the higher number of end nodes. I'll pass to my teammate Zion.
Hello, everyone. Okay, can you hear me? I guess so, right?
Yes, yes.
Okay, we are going to compare the models with using all variables and the model with using the 6 selected variables. And we can see that the important variables for both models will be the same, which are polyuria, polydipsia, and gender. So we can conclude that polyuria and polydipsia are the important symptoms to determine that one have diabetes or not. And also the gender is one of the important features that determine the one has diabetes or not. But there are differences between the variables, between the models for the variables that use for split. And as you can see, for the same variables will be polyuria, polydipsia, and gender, but the remaining one will be the different one, which are for using all variables which are itching, delay healing, muscle stiffness, alopecia. But for the selected 6 variables will be the age, standard weight loss, and partial paralysis. But you can see that the accuracy, precision, sensitivity, and specification, the model with using all variables generally have higher accuracy, precision, sensitivity, and specification compared to selected 6 variables. So the model will be selected for our study will be the model with using all variables. Farhana, next. So we are going to interpret our result based on the best model. And you can see that when one has polyuria, you starting from the node 1, and if he or she have polydipsia, which is continued to node 2, and it is 100% certain that he or she has diabetes. So in the sample size is about 141 of them. And next. And when one does not have polyuria, which is at the right side of the from node 1 to node 3, and continue to from node 3 to node 7, which is gender is male. This implies that if the one is a male, then when he does not have polydipsia, which is from the node 7, the right hand side of the node 7, it is 93% certain that there's typo there. It is 93% certain that he does not have diabetes. So this is our important findings from the decision tree. And we also can find that there are less important symptoms to determine one have diabetes or not, which are itching. And so you can see that if the person have polyuria, polydipsia, and itching, is also 100% certain that one have diabetes. And followed by if the person which have B1, which are which are muscle stiffness. Yeah, which are muscle stiffness also can say 100% certain that the person have diabetes. While if the person do not have polyuria and the person is a female, but the person do not have alopecia, the person still has a certain possibility that have diabetes. And that's the interpretation of the decision tree. And I will pass the presentation to my teammate.
Hello, I'm Suchi. I will continue. Can you hear my voice clearly?
Yes.
But need to speak louder.
Okay. Okay. So the conclusion, to avoid overfitting and complex tree, we select the model with pruning value of 1.5 instead of 0.5. Furthermore, we can see that from using pruning value of 0.5, it contains nodes with no significant split variables, the one that is circled with the dashed line. And from the classification tree, we have found that the 3 variables, which are polyuria, polydipsia, and gender, are important features in diagnosing diabetes. So this is consistent with our results from the first assignment, which are using chi-square and PCA. Next, the limitation. First is our sampling method is only done once, so we think it is not random enough. We could, our recommendation, we could repeat the sampling with a different set of randomized data to validate the model. For example, we can use a different ratio of training versus testing set. Next, the selection of decision tree is not random enough because we do not do all the possible pruning level. Next, Farhana. And then lastly, the recommendation, we could further analyze using random forests. And I mentioned this one already, we can repeat the sampling using different set of randomized data. I think that's all. And lastly, this is our reference. That's all from us.
Dr. Kaya.
Okay. Okay. Yeah. Thanks for your presentation. You define. Can you go back to your evaluation metrics? You defined. Okay. Go further back. When I think the first few slides. The right side. Accuracy, precision, sensitivity. How do you define precision?
Precision actually is the the precision is the number of correctly predicted for the positive case over the total positive case predicted.
Okay.
Yeah.
Then what is this thing called specification?
Specification is correctly labeled predict as negative. I mean negative when the person is false, which is don't have diabetes.
Is it called specification?
I think so. I saw it is specification.
Or did I write that?
Pardon?
Did I write something like that before?
No, but I just include that. I remember the doctor is including sensitivity. Oh, sorry, specificity.
Yeah, I think.
Yeah. Okay. Sorry, doctor.
This one, okay, so this one is basically so this is your truth. This is your prediction, right? So your precision is you are taking the row here, right? You're taking this value and dividing by the total here, right? Correct? That's your precision, right? Your sensitivity is going by the column, right?
Yeah.
Okay. Then okay. Can you go for a few more slides? Okay. What's the class ratio like in your data set? What's the percentage of male and female?
Male and female.
So
I cannot record that, but I just managed to remember is for the positive and negative.
so what's the positive negative? The ratio.
For the positive and negative is about 4 to 6. 4 to 6.
Okay, it's quite balanced. But I recall there were actually more females who were diabetic, right?
Yeah.
I think we sort of discussed that.
Yeah.
Because the males, they do physical work, so they have some compensation effect. That is actually not related to their gender, But the gender is more like a kind of a proxy for physical work. So here you might want to discuss that that part, because I think based on just the fact that someone is male or female does not really it's not really predictive of, you can't just say that, because this pattern, right, may change in different countries, you know. In different countries where the male and females are more or less working on sedentary kind of jobs, then you may find that the incidence of diabetes may be more or less the same among males and females, right?
Yeah, I saw the studies as well.
So, but in this case, it seems like the females are more susceptible. But I think it's, yeah, that's why you have to relate it. You can put it in the discussion, because you want to make it clear, right? Because some of these variables, they are basically proxy for something else, right? Which you can actually maybe put in the discussion later in your own reports.
Okay. Doctor, if the male and female actually imbalance, right? So we need to deal with it, right?
No, because you are not. Is the imbalanceness is with respect to the target variable, your response variable. This is not a target variable, right? So
yeah. Our target variable will be positive and negative, which are the class.
Yeah, that one is more or less balanced, so you don't need to do anything.
Okay, understand.
That also explains why your result for equal prior and estimated prior are about the same.
Yeah.
Because yeah, actually not much point doing it, because equal prior means you assume half. The other is they just use the
sample to estimate, right?
Yeah, the sample proportion. So since it's more or less balanced.
Because I have briefly gone through for the class ratio for the testing and trading set, and as it is generated by randomly, I saw even they generate up to 7:3. That's why I thought of comparing equal prior and estimated prior. Yeah.
So okay, basically your pruning levels, that's your SE lah, right?
Yeah.
Number SE. So okay, when you make your pruning very large, so what kind of models you get? You basically get very simple models, isn't it?
Yeah, I did try until pruning level with 10 SE, which is using polyurea only. If you have polyurea, then you have diabetes, and you don't have polyurea, then you don't have diabetes. Yeah.
So yeah, with that kind of extreme pruning, that means your polyurea must be really important to remain.
Yeah.
After you extremely prune the tree, it still remains, right? So it must mean that it is actually very important. Yeah. So yeah, sometimes people can also find out how important is the variable by they do some extreme pruning, and the things that still remain are really important.
I see. Because we discussed whether we need to include the extreme case or not, but we found that it may be not necessary.
Yeah. Well, that will kind of like help confirm that. But you already find the polyurea as somewhere at the root node, right?
Yeah. It's the root node.
So that already is, well, I mean, it's just sort of reinforces your result.
Okay, understood.
So at the end, you suggested what, random forest?
Yeah.
Okay, so if you use random forest, then of course your prediction results will improve. But how would you actually present the result from random forest to the doctors? For example, now you are trying to convince the doctors to accept your result, right? And
Yeah.
the random forest. So random forest, you're using, your result is based on using multiple trees and using the majority vote from the trees to get the predict the metrics, right? So how would you, even though you get some better results, but how do you sell that to the doctors? How do you sell the result to the doctors?
The selling point of random forest, I think, will be the higher precision only. But if speaking of the result, which is simple, I mean, the decision tree will present a simpler way to determine one has diabetes or not. Then decision tree will be better lah. The only selling point I can talk of random forest will be the prediction will be better.
Actually, you can try the random forest in guide. Did you try it?
No,
You might
because I rushing other assignment.
You can actually, since you still have a bit of time,
Yeah, I saw that.
so you might as well run it and just to see how much more you can squeeze from the model.
Okay.
Actually, one way to sell the random forest to the doctors is that, okay, so you will show the result on the single tree, okay, and then the single tree is just to point out that, you know, if you use a single tree, then these are the variables that are important in predicting diabetes status, right? So you can show, because when you show a single tree, it's very explicit, right?
Yeah.
But then you can also say, that, okay, so we know that these are the variables that are important. So the doctors will use their domain knowledge to assess whether those variables are the ones that they always also use without using this data, right, based on their own experience.
I think in their mind, actually, they perform decision tree.
Yeah, but their decision tree is not data driven.
Yeah.
It's kind of like based on some common sense. So they cannot give you, they will just draw the decision tree, but it's like a qualitative, in a kind of like based on a kind of like a compilation of experience across many people. So somebody will sketch something like this, and then
Yeah.
so it's not a very, it's not data driven, but it's kind of like a semi data driven method where the data is not very explicit, right? So
Yeah.
you have explicit data, so you can actually it's nice that it is actually matching their experience, and then you can say that, okay, so you have this classification model that where these variables are useful for prediction. And then the random forest is basically just some kind of a further optimization of your model to improve the prediction result, that's all. But more or less, it is still using the variables that you picked up in your single tree. Okay, so with that, they are more inclined to, because they can see something concrete, right? So you are doing the best of both worlds. First, you show them something concrete. Then you say that the random forest is just basically some extra optimization step to further improve the prediction results. But the variables that you use are more or less will be, is basically subsets of, more or less subsets of the variables that you already see in that single tree.
Okay.
In that case, I mean, like for actual application, then of course you might want to use the random forest. But then for explanation, then you can fall back on the single tree, right?
Yeah.
Because random forest, if you just talk about random forest, it's too abstract for people. So if it's abstract for the doctors, they will not apply it. People in medicine are very suspicious of non-transparent methods. So that's some comments about that.
Okay, thank you, Doctor.
So, okay. Okay, so thanks for the presentation. And then let's move on to the next group.
Maybe our group.
Okay, go ahead.
Okay, yeah. So give me a second to share screen. Share screen is, this is screen 2. Can you see my screen now?
Yes, can see.
Yes. Okay. So this would be the. Okay. So maybe I let Yuzing to start the introduction. Yuzing, are you here?
Can you hear me?
Yes.
Okay, thank you. Hello, everyone. Our topic is about hypothesis C classification problem. Our team members are Chen, Kim, Aliyah, and me. Next, the part 1 is introduction. The disease caused by the hepatitis C virus. The hepatitis C virus is a blood-borne virus. Globally, estimatedly, 71 million people are diagnosed with chronic hepatitis C. A large number of the chronically infected people will develop cirrhosis or liver cancer. In 2016, approximately 399,000 people died from hepatitis C, mostly from cirrhosis and hepatocellular carcinoma. Next, this stage of liver failure, inflammation, fibrosis, cirrhosis. The last one is stage liver disease. The data set was obtained from sample of 615 people, which are categorized into blood donor, cirrhosis, fibrosis, hypothesis, and suspect blood donor. It consists of 20 explanatory variables, which are sex, age, ARB, ARP, ART, AST, BIL, CT, CHOL, CREA, GDT, and PROT. The next part is methodology. Aliyah?
All right, now moving on to the methodology section. Our main focus is on the implementation of SVM algorithms using different kernels. And these are the overall steps in our approach, starting from the pre-processing techniques that had been discussed in assignment 1. Next slide, please. In assignment 1, we performed PCA and also recursive feature elimination for the feature selection. And we picked the top 5 variables that we obtained from the recursive feature elimination technique to create the models. Next, we split the data set into trained data set and also valid data set. Next one, please. All right, so now as you can see here, we have imbalanced class ratio. So next one. So the first strategy is to handle the imbalanced class ratio using rows and also smoke techniques. Then we will get 3 data sets. The first one is without the imbalanced class ratio handling, and the second one is using rows technique, and the third one is using smoke technique. Then we implemented SVM algorithms using 4 different kernels on these 3 data sets. We use cos1 or 1000 for linear kernel, degree 2 or 3 for polynomial kernel, and cos1 or 1000
for radial kernel. Next, then we evaluate the model, this slide. Next, we evaluate the model performance using specificity, sensitivity, and also balance accuracy. Next slide. I pass to Jake.
Right. Yeah. So the methods of handling the unbalanced class ratio is actually using Rowe's mode of class weight, where Rowe stands for the random oversampling examples and SMOD stand for synthetic minority oversampling techniques. Both of these techniques is actually handling this particular unbalanced class ratio from the data method, which then you can do some oversampling or you can do some undersampling. And then the one that is class weight is actually handled it from the algorithm way. That means it's like, let's say you are predicting this hepatitis, right? So we have lesser samples there. So if you have impose a heavier cost to let the model know that it's more important compared to the one that is generally in the blood donor itself. Sorry. So next it will be the parameter tuning. The parameter that we tune is actually like what Alia mentioned just now. Just that we didn't do too much of parameter tuning due to the reason that we have 4 kernels here and we are trying different kernels to observe what patterns is there. So that's why it's there. And then the cost-wise, it's actually when there are small costs, that means it create a larger soft margin, which allow more misclassification. And the large cost implement that the small margin, which permit fewer classification, which is the C equals to 1 and 1000 just now. And then for the training data set, because we have a few training data set as we mentioned just now, and also we went through a PCA and RFE to check about what kind of features we should select. So we have one data set that is in all features, and the second one will be the selected feature, and third one will be on the row selected features. We do try on all features, but it doesn't work out. That's why I didn't put it here. As mode-wise, all features is good enough, and selected features seems like having some issues over there. I guess it's because of the technique that we created the samples using the oversampling part actually caused some sort of bias within the sample. So we need to take some of the features for this part. And you can see that here we actually did an oversampling and then we do another undersampling. And for this part, we do oversampling, which then it's more than the current one. And we also did some undersampling over here. So how do we do it is actually on the next slide. Sorry. This is the result already. So we conducted about different combinations to see like what kind of things is actually good, what kind of things is bad. And we found that generally linear is actually sufficient enough, but then because we can see we allow lesser classification, that's why, I mean lesser misclassification, that's why it's having higher accuracy. And from here we can see that SMOD or rows itself is kind of like, I would say it's not really too helpful comparatively, like a top 5 model itself, they have 3 4s and stuff. And then like here the only one that is using all features. And the class weight wise is all true generally to help the model to understand better. And then the top 5 itself is actually linear and also radial. So the balanced accuracy is actually sensitivity plus specificity over 2. So that's why please don't confuse it with the normal accuracy itself. It's not that one. Next, it will be the validation performance itself. So from our model number 2 is a linear kernel with no oversampling and with selected features is C equals to 1. We can see that it's actually predicting quite well on terms of like the positive classes, and they only make one mistake over there. However, from this part, we can see they make a lot of mistake on the negative classes. So this one, that's why we remain this particular model to observe whether is there any other model that is better. And model number 3 would be the radial kernel with small oversampling methods, 1:6 ratio. That means for each class 1 itself, we will generate another 6 samples. So total it will be 7 there. And then we're undersampling it. That means like if for how many oversampling of samples that we oversample, we only take that part. So let's say I generated another 314 of the samples. I will undersample my particular majority class to 314 only. And it's taking all features, of course. So here we can see it's quite balanced. So that's why we put this one of the model, which is the model number 3 over here. Next, we'll be observing our model number 4 itself, which is the linear kernel with rows oversampling and selected features. So we can see here it's about similar with our model performance tool just now, just that it have worse predicting on the positive class and better predicting on the negative class actually. So this would be the comparison of the selected 3 model performance. Let's look at the validation sample itself originally, like how much do we have for cirrhosis, thrombosis, hepatitis, and also blood donor. So from this part, we can see that it's like the model 2 itself, we're having about 100% of cirrhosis and fibrosis to correctly classify them. But then when it comes to hepatitis, it seems like it's not so good. And for the model 3 itself, it seems balanced in overall. And for model 4, it's actually, you can see like some sort of misclassification happening over the part where the hepatitis itself is not that good. So in our, so this one would be the suspect blood donor because we don't have any labels, right? So we would like to see whether if we use our model to predict what will happen, like what kind of results that we will get. So we can see like most of them is actually positive. And then in the linear cases, somehow both of them giving the same result. But for the radial one, it's actually all positive. So in conclusion, I will let Alia to be presenting.
All right, so based on the validation performance, we would recommend the models number 2, 3, and 4 because for model number 2, it works well for the severe patient but having a higher false positive rate. For model number 3, it works well for non-severe patient but having a higher false negative rate. And for model number 4, it works better than model 2, but having a higher false negative rate. So for this data set, SMOTE works better with all features and ROSE works better with the selected features. And we also conclude that adjusting the class weight is very important and polynomial kernel does not have a good performance. So for future work, we can do a grid search to tune other parameters like gamma and also with different feature set with some feature engineer methods. That's all. Thank you.
Okay, thanks for the presentation. Okay, so do you have do you have results where you basically don't do any you didn't do any sort of adjustment for the class ratio and just simply
sorry, actually we apply all the class ratio itself. So that means for the model, let me take a look on the results itself. So from here, you can see that the class ratio is all applied, and then the class ratio is based on the particular training data set, this part. So how much that we have there, we will implement that as a class weight.
So this one is the, your positive samples are what? Does that include?
Yes, it includes those hepatitis, fibrosis, and cirrhosis as well. Yep.
Okay, group together.
if let's say we ignore those samples, right, we actually have about 24 for hepatitis only. Yep.
So altogether you have 51.
Should be 75, I think.
75.
Yep.
Okay. So if you just go by majority class prediction, what is the accuracy?
Go by the majority class prediction as in
So basically take
without using the weights, right?
Yeah, basically you just take the number of positive cases divided by the sample size. What is that? What percentage? You can just do a quick calculation.
Oh yeah, I don't have it. Yeah, let me find my calculator. So it would be measured. So I divide. May I know what's the question again? Sorry.
You just divide 533 with the total, right? So that would be
533. Yeah.
total. Just now it was what, 75?
Yep. Yep. 75. Yes. So it would be 76% of the positive sample. Yes. I mean the negative sample. Sorry.
Huh? 76%? No, I mean
you are asking
all the data.
Sorry, sir. I like your question actually. Yep.
If you divide,
so you are asking
over 533 plus 70.
Yeah, it's 76 from my end here. Oh, sorry. Yeah, I know why, because I forget to bring that. Yep. Okay. Yep. So it would be 87%, 88%, at 87.66.
Okay. So if you look at your results, you can actually push further. Can you show your results?
Yep.
This is the training on the result is on the training set or test set?
It's on the on the test set.
Test set.
Yep.
The best one has 95%.
Yeah, but I don't recommend with the 95 one.
So this one you are not doing oversampling, and you.
Yeah, I'm not doing oversampling for this part. Yep.
Okay, and you already get pretty good results.
Yes, because we applied class weight in general to the model itself. So the model actually know that they will need to impose the heavier cost there to the part of the positive class.
So is that done? What is the they do unequal cost misclassification cost?
They do the unequal cost. I wouldn't say misclassification cost. It's like during the loss function itself, they put the coefficient. In general, we always put 1 to 1, right?
Yeah.
So they input the coefficient to the particular loss that, which is like, let's say, giving an example, like let's say predicting the correctly for the class 1, I would get 1 originally. Right now I will get 6, something like that.
Okay, it's a higher penalty for mispredicting
the
minority class, right?
Yep.
Okay, so that's already doing very well.
Yep.
Whereas if you do those kind of more sophisticated methods, you're basically not doing that well.
Yeah, if we are using any like polynomial, somehow it doesn't work out in this data set. You can see that it's always, I mean, among the same kind of settings, when we change the kernel to polynomial, especially polynomial 2, it always fell. The result always like dropping, like even we handle the class weights. So it's worse than that sometimes.
Okay. So what's your recommendation?
My recommendation would be, because like, let's say these are to the hospital itself. So whether the cost get because disease is more, or the cost of getting sued because you identify wrongly giving a false alarm to him. So that's why I leave the 3 models here for anyone to choose. Like, let's say if they feel the cost of getting sued because of the false alarm is higher, then they will go for the one that is in model, false alarm would be in model 3. So the one that is like, let's say they
Actually,
think that.
What does it mean when you say works well for the severe patient, works well for the non-severe patient? What does it mean?
Yeah, because the hepatitis, right, from the UCI machine learning repository, they mentioned that the most severe cases is cirrhosis, and it comes to cirrhosis, and it comes to hepatitis. So it's like developing based on this manner. So when we are trying to like drill down on the model performance.
Cirrhosis is the early stage.
No, cirrhosis is the late stage.
Late stage. So if you you mean when you say severe means?
Yep, it's in cirrhosis already.
Cirrhosis, all right. So predicting the cirrhosis would be more important, you're saying?
Yeah, I'm saying that if it's severe patient, then they're able to detect it. It's common, right? If they are not able to detect it, then it's a problem. So, but then it will raise more false alarm when it comes to the other end. So it's like a bit hard to balance between this part.
But then usually people who are at the cirrhosis stage,
it's already in hospital actually.
They are already so sick that you don't really need to predict them. They already will manifest themselves.
Yes.
At a very sick person, so you will detect them anyway, because so it's also a bit too late to help them actually.
Yep.
So wouldn't
if in that case we will suggest model 3 then.
So would it be better if you catch someone at the early stage?
Yes.
Because an early stage person, they may not have any symptoms. So if you can catch these people, because I think the reason why you are catching all this, you see your models can catch the cirrhosis very well, is because usually when people are so sick already, all their blood variables are very extreme already. So that's why even a linear model can capture that. You know, they're so extreme, right? So okay. Right, but then actually, I would also say maybe not. The result may not be very conclusive to say which model is good, because the correctly classified is from 5, 6, 7. Right? They all differ by about just roughly 1 or 2 cases.
Yeah.
So it's also not very conclusive.
Yep.
So I would say maybe all these 3 models may be reasonable candidates, but
not conclusion. Yes.
Really,
it will be
say that one is. I mean, like in a statistical sense, right? Yeah, sure. Like it managed to predict a few more, but correctly. But since the number of validation samples is not that many anyway, so we will just present it like that and then say, well, these 3 models seem to be reasonable, and not say too much about it further.
Okay.
Yeah, but of course, if you really have to pick one, then you will just go with maybe model 3. possibly.
Yep.
Or maybe 2. I guess maybe 2 may be better. 2 may be better. Okay.
Yeah, I'm having a dilemma to choose a model
Probably 2,
actually.
because yeah, on average it just looks better, I guess.
Yep.
Okay. So thanks for your presentation, Jake.
Thank you, Dr. Khan.
Okay. So maybe we can follow up with also the hepatitis C group, the next one. You can stop sharing, Jake.
Okay, in my group. Can you see my screen?
Yes.
Okay, Wenfeng, it's your turn.
Okay. Yeah, okay, just go ahead.
Wenfeng?
Okay. Just give Wenfeng some time.
Good evening, everyone. So I'll be presenting our group assignment today. So the title of wait, Sulu, can you put it in the full screen mode?
Okay.
Okay, thank you. All right. So the title of our assignment is the identification of hepatitis C infection using the artificial neural network ANN. So my team consists of me, Chen Yi, Sulu, and supervised by Dr. Kang. All right, so the agenda of my presentation of today is I will start off with a recap, and then I will talk a bit on the data, and then we'll go into the methodology, and then after that we will broadcast our results, and then we will discuss on the results, and also at the end we will provide some recommendation. All right, so a brief recap. So fibrosis is the first stage of liver scarring due to liver injury. And when scarring deteriorates and damages liver function, the late stage, it becomes cirrhosis. So there are many reasons for these conditions. And one of it is the hepatitis C infection. So our goal today of this research is to separate the people with hepatitis C. Okay, so the markers of the hepatitis C virus in human blood at early stage till development of fibrosis is rather weak. And our data set consists of 615 observations, 13 variables, and we have only one class label with 5 different categories: the blood donor, suspect blood donor, hepatitis, fibrosis, and cirrhosis. And we have 12 features to predict this the class variable, which is we have 2 categorical variable, the age and sex, and also 10 continuous variable, which are all the enzymes in human blood. All right, so first of all, we started with some data pre-processing. So we checked the missing data, and we found that out of there's 26 rows, which consists of 31 missing values. All right. So what we did is we checked on the distributions of all these missing values, and we found that out of it, there's like about 43% is quite high in the fibrosis, and also in the hepatitis, it has like 70%, which is our main target today. And so we decided not to remove them. So we decided to replace them with the median. All right, and then after that, after we have examined the types of data, we will start some data pre-processing. So first of all, we encode the categorical data, the sex and category, using the one hot encode, and then for the continuous data, we standardize it using the min-max approach as shown in this formula, and then we split the data to a ratio of 70:30 for training and testing purposes.
Okay, for data exploration, we check the data ratio before splitting the data, and figure 1 shows the proportion of each category before splitting, and it is obviously, we can see that the data is imbalanced, and out of 615 samples, the blood donors already takes up more than 85%, and cirrhosis, fibrosis, hepatitis, and suspect blood donor do not take up even more than 5% respectively. And so we perform undersampling by selecting 19 samples randomly without replacement from blood donor category, and the difference of the proportion between each category is smaller as seen in the figure 2. Okay, for the results, the left figure shows the weights among layers, and we choose sigmoid function as the activate functions, and we use 5 nodes and 2 nodes, 2 hidden layers, and each sample goes through neural networks and has responding probabilities for 5 categories. Then a sample will be classified into the category with highest probability.
We use ANM to classify the samples in testing dataset. Then the outputs is shown in this table. As we can see in the number at diagonal means right classification. So we can calculate the overall accuracy is equal to the sum of diagonal numbers divided by the all samples in testing dataset is approximately equal to 0.88. And actually is a quite good result. Then let's look at table 2. It shows the corresponding proportion and accuracy of 5 categories. We can see ANM model has over 98% accuracy to classify the category blood donor. For categories like cirrhosis, fibrosis, and hepatitis, the accuracy is not very good, but still higher, much higher than their proportion. Because if we just randomly guess a sample's category, their accuracy will approach to its proportion. ANM model has higher accuracy than their proportion. It indicates ANM model does work. For suspect blood donor, the accuracy is equal to 0. In testing dataset, except blood donor, other category only have a few samples. ANN's accuracy for suspect blood donor is 0. Maybe it's because ANN model cannot capture enough hidden characters due to its small quantities. Another reason may be cases in suspect blood donor is normal or has suffered from other diseases but need further checking. We use undersampling method to deal with Chinese datasets. It means we actually throw away a lot of original information and useful information. That's all about our presentation. Thank you.
Okay, thanks, Silu. Can I just look at the slide, the result on slide 10? 10.
Okay.
So this is the result on the test data.
Yes.
The training, so the slide 11. 11.
Okay.
This is the result on the
testing data set too.
So how did you compute the accuracy? You are
just use the number.
Look at within the column.
Yeah.
So that is actually not accuracy. That will be your conditional sensitivity.
Yes.
So I think the term accuracy is not correct, because accuracy you already said it's 88%.
Yeah, it's overall accuracy.
Yeah. So, but then this is actually not the it cannot be defined as an accuracy, because this one you are okay. You go back to slide 10. So basically, you condition on the blood donor, that column, right? And then you take like, okay, like for example, for blood donor, you have total is 148.
Yeah.
So then you take 146, you divide by 148, right?
Yeah.
Yeah. So this is something like your sensitivity, but it's sensitivity for blood donor.
Okay.
Okay. So when you do the when you kind of like condition on the columns, right? So that's not actually accuracy. It's basically sensitivity. Basically, it's a sensitivity for blood donor, sensitivity for cirrhosis, sensitivity for fibrosis, and so on. Okay.
Okay.
Yeah. So I think the terminology is a bit misleading there. And then of course, since it's a conditional probability, it would be a bit difficult to compare with the proportion, like what you're trying to do here. Because there are different things, right? Because your proportion is computed by dividing over the total, right? Whereas your so-called accuracy here is basically a conditional probability. So unfortunately, the comparison is a little bit it's not on an equal footing, you know, the comparison.
Yeah.
You can fix that, all right? And then you say something about one hot and cold. What's that?
So one hot and cold is actually just changing the data to the binary form 0 and 1. So let's say you have classes of 5, so you have like 5 columns with 001, 0010, something like that.
Can you make it clearer? Okay, let's look at your. You have. So you what? You have.
It's in data.
You have 2 categorical variables. One is.
Yep.
So. Your age is age categorical?
Yes, but I did not one hot and cold age. Age is somehow in the form like ordinal.
I think age is not given as some age group, right? It's just age itself, right?
Yeah. There's no like months in between, so it's just years.
Yeah. So then it's not. Then it's just a continuous variable, right? Why would it be categorical?
Right. I mean the reason why I park it under categorical is I felt that because there's no it's not within a ratio, so and it has no like continuous scale is somehow it's like discrete.
Well,
And-
you can treat it as a continuous. I think there wouldn't be. Well, of course, I mean, like we just basically report age as a discrete number because basically we don't want to tell people like I have lived for 3,650 days, right? At that scale, you could. I mean, like you could make it continuous by basically considering the scale to some very fine level, isn't it? Right. It's just that we don't do that for convenience purpose. So, but for analysis, I think we can perfectly treat it as a continuous, even though it's kind of like moving in integers.
All right, noted.
So in that case, you are just saying that your sex, you just turn it to 0 and 1.
Yep.
So okay. So then you normalize your data. Okay. So I don't really know how when you categorize your age, how would it become, like so-called one hot and cold.
Okay, so basically it will have two columns, one for female and one for male. So if it's for that particular sample, for one sample, if it's a male, the female will have a value of 0 and male have a value of 1. So if it's female, then the female column will have a value of 1 and the male column will have a 0.
I'm just trying to, okay, let me just see if I can write something. Okay, I'm just going to sketch something. So you're saying, okay, you're saying something like this. So this is your sex column. So okay, this is the original one. Let's say it's a female. They have male. So when you do your what is it called? One
hot and cold.
One hot. I don't know about that term. Okay. Anyway, yeah, there are a lot of these tricks in machine learning. But okay, so then what do you say? How does it become?
All right, so I will have I will break the sex into two columns. So basically, one column is for female and another column is for male.
And then you put it as 1, 0.
Yes. And then for the second observation, I will have it as 0, 1.
Oh, okay. So
in statistics, it's basically is like a dummy variable.
So for example, you have 3 levels. Let's say female, male, and the other is unknown. So like
we'll have,
yeah. So then you would code like this.
Yes, correct.
And then means your data set will have additional, like after these variables you have you will have your FMU, right?
Mm-hmm.
You have additional columns like that, right?
Yes.
Okay. That's one way to do it. But of course, at the downside of this is that it will expand your dimension. Your data dimension will increase. Then how about your age? I wonder how you do that, because your age will be like all sorts, right? So I wonder how would that. It's still okay for sex in your case, but how would that affect your age?
For age, basically I did not do this transformation. I just treat it as something like continuous.
So then you didn't actually put it here. Actually here lah.
I mean, in the way of treating it is yep, but
okay.
I mean maybe there's some blur boundary between whether it's a categorical or continuous, so which causes why I put it under categorical.
Yep. So okay, if you put it here, then you do your min max normalization.
Yes.
Okay, so so you're doing random undersampling. How many times did you do it? Once?
Yes, we did it once.
Wouldn't you need to do it many times and average the result?
Um, I mean, yes, it is, but I mean, we did try a few times, and then we got like almost pretty same results, and yeah, that's a good suggestion. So we will, I mean, further enhance the report with the
Okay.
with the average.
Okay, then since you have already learned ensemble methods, right?
Yep.
Ensemble methods basically is like you have okay, of course the way we do ensemble methods that we usually have a weak learner, and we build a stronger learner by combining weak learners, right? But related idea here is when you do your undersampling, your undersampling is that you basically you have your majority class here. So every time you do an undersampling, okay, then you have your neural network model, right? Which you can make a prediction, right? I mean, like you can train. Let me see. You will train. So you have neural network model. So this is model 1. Okay, train using some random subset from your undersampling, right?
Right.
Then you have maybe another random sample, so you can build model 2, right?
Yep.
Model 3, model 4, model 5. So you can. That's why I was trying to say you could build a lot of models, right?
Yep.
Okay. And then now, if you use the idea ensemble methods, right? How would you combine all these models to build a single model? So you have your test data here. How would you do that? Okay, group members can help to ask, right? Answer, right? So basically now what happens is that you got model 1, and then basically you put in your test data here, and then you make your predictions, right?
Yep.
Okay. So I'm asking you, if you repeat this random undersampling multiple times, let's say you repeat it 1,000 times, you will get 1,000 models here, correct?
Correct.
So how do you combine the result from all these 1,000 models to produce a more robust result?
Average their weights.
Average, can you be clearer? How would you average the class prediction?
Maybe we have a lot of ways. Maybe we can just sum their weights and divide the number of models.
No, but then the models will be all different. Your okay, so okay, fine. Your architecture will be the same, but of course your weights will all be different. So if you use the idea from ensemble methods, what would you arrive at? What sort of solution would you arrive at?
I mean, I think it's something like it combines the bootstrapping and some form of aggregation. So I think they did a few rounds of bootstrapping, and then they aggregate the results of the bootstrap to get like the final model. Am I right? Instead of just one bootstrap.
Okay, here of course you could. Okay, here you are not bootstrapping. Well, you're not bootstrapping. You're kind of like because it doesn't really here you're kind of like doing some kind of permutation, because you're not actually doing bootstrapping, because bootstrapping you can repeat a sample, right? The sample can appear more than once. Here it's not appearing more than once in each model. Okay, you just recall, right? When you do random forest, right? So each of the trees, what are they doing? Tree 1, tree 2. Let's say you do 1,000 trees. What are each trees doing? So when you have a sample going in, how does the random forest make a decision? So you got multiple trees, right? You got 1,000 trees here. So you put in a sample, tree 1 will predict, say, plus, right?
Yep.
Maybe tree 2 will also be plus, but the other trees, maybe some of them minus, some of them plus, right? So at the end, how do you decide here? You get all sorts of predictions. So you come up with one prediction at the end. So how is it made?
I think we decide on, it will randomly select like a model based on like a random select of features, and then it will decide based on the best split, I guess.
No, yeah, sure. So these are all the trees already, right? So basically you put in the test data, so row by row. So it will, these are the predictions for one particular test sample, right? So let's say, so each of the tree will give a different prediction. So at the end, you have to report, you have to summarize all these predictions into one prediction. So how do you decide on that?
Maybe look at the majority.
Yeah, it's a majority vote, right? It uses the majority vote. It's a very straightforward idea. So it's like it uses a democracy. Okay. So you
All
got
right.
1,000. I mean, like usually they will do yeah, probably the numbers here should be something that is an odd number, because otherwise you might have ties. So anyway, so you have majority, you do a majority vote. All right, and so here is the same, right? You could repeat this. So all the models will make a prediction, maybe a plus here, minus here, plus here, minus here. So you do a majority vote lah.
All right.
That's what I was trying to see, whether you are able to connect it to the idea. But of course, on support methods, they is slightly different. The idea here is the majority vote lah. If you got multiple models, then you use the majority vote from the multiple models to produce something that's more robust. Because currently now, what you are doing is you're only doing one particular instance, this model, you know, and then you're making prediction. Okay, so it's possible that you actually you can basically do many more, yeah. Because since your neural network method is already abstract, you see, it's already a black box.
Mm-hmm.
Are you able to know which variable is important in your model?
I think no, because it's a neural network. So actually all the variables will contribute to the final prediction.
Okay.
Yeah.
So the doctors are going to get very puzzled with this model. Yeah, your model will predict something, but when asked, how does it do the prediction? No answer can be given. Right, because the model is abstract, right? It's a black box model.
Yep.
Yeah. Okay. So I hope for the other students, when you see this, you can take note of the strength and some limitations of the methods. Of course, you're not going to be penalized just because you use a model that's not. Yeah, I don't look at it like that, right? I mean, like as long as you know how to use the model and you are able to lay out its strengths and weaknesses, then it's all judged on equal footing, right? Because this is just an academic exercise, right? But of course, if you go out to do actual machine learning work, then you have to pick the model that is better at explaining things. But it all depends. But neural network, in some situations when you only need to make predictions and don't care about explanation, you can still go ahead, right? Okay.
All right.
Okay.
Okay. Thank you.
Okay, thank you. Okay. So now we will take a break at 7:30. All right. We come back around 8:10. All right.
Okay.
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 Can you see my screen?
Yes.
Okay.
Okay, hi everyone. Good evening. Today we are going to present predictive analytics using knife-based classification on my protein expression dataset. Okay, to start, this is a quote by a Nobel Prize laureate receiver, Ronald Coase. He once said, "Torture the data and it will confess to anything." Okay, next. Okay, now onto the introduction part. Knife-based is a supervised learning method. So supervised learning is used when data instances belong to a set of predetermined classes or class labels. So their goal is to build a general model that can subsequently be used to classify new, unlabeled, or simply called the testing data instances. Our dataset, which is the mice protein expression dataset, consists of the expression levels of 77 protein modifications that produce detectable signals in the nuclear fraction of cortex. There were 38 control mice and 34 trisomic mice for a total of 72 mice. Okay, in summary, there are 8 combinations in our dataset, and for the total listing of mouse ID is 72 mice or 72 samples. So this means that each class would have 7 to 10 mice. Due to the small sample size situation here, we developed 3 knife-based classification for the listed classes below. So now it becomes a binary classification because, as you can see here, each class contains 2 variables. Okay, now Jeff will continue on the following part.
Oh yeah. Okay, hi everyone. So based on our previous study, we found that fancy cleaning methods doesn't help to separate out the data. So we are using the most basic one, which is the mean, to get the application of it. On top of that is also because having mean is like easy to understand, right? When people ask what does it mean for that particular features, and for data imputation, yeah, mean as well. And then it's also partly because the naive bias can't handle missing value well, so it has to be impute in something and then we just mean. And data normalization is not required, so we ignore that. Next. Then it's just a go through on the PCA results, and by a glance we can see, well, behavior is the one that having the good features. So we have the mindset of don't have a high expectation already on the genotype and treatments. But let's see what we can do also for naive-based. Next. Right, so we select the most important features to be fit into the naive-based algorithm based on the t-test result, and then we have chosen 2 for each of it. Yep, next. And then this is our method of doing before we do the classifier. We set the objective to do the binary classification only by classifying the genotypes, right? Then we train and validate using leave one out cross validation. The reason why we use this is because the sample is very slow. Like we have only 72 data points only, so that's why having multiple trial of like training each time and fit and test for one sample one by one is quite feasible. And we use this method to choose our models. Then we apply the model to 25% of the sample data, and just as a purpose to see how it looks like. So next, I pass to my teammate.
Okay, so this is the result for the behavior. So while using the train test bit with ratio 0.75 approach, we can see that we can achieve an accuracy of 100%. And this is the decision boundary plot on this the model. And for the leave one out cross validation approach, so there is three parameter. There's three tuning parameters. So we will the model will for the carrot package, it will automatically choose the best model, which is the FL is the Laplace smoothing, and the use kernel is false. If the use kernel is equal to false, then it is the normal density estimation. If equals to true, then it is the kernel density estimation. And adjust is the bandwidth used for the KDE. So this parameter is only used when the use kernel is equal to true. And it represents the spread of the KDE density estimation. So we can see that the accuracy is 0.986, which is slightly lower than the train test bed approach. And we can see that the decision boundary is almost the same as the train test bed approach. And then for the result of the treatment, the train test bed approach achieved a 61% accuracy, and this is the decision boundary, which is not quite good, and there are many random points scattered around. And for the leave one out cross validation approach, the Laplace smoothing is equal to 0, and the best model is for the Laplace smoothing equal to 0, and the use kernel is equal to true, and adjust is equal to 1. So the best model is the kernel density estimation, which is 57% of accuracy, and this is the decision boundary for the plot. So the decision boundary is quite weird in the shape compared to the train test bed approach. So this is the result for the genotype, and the accuracy is the same as the treatment, which is the 61%, and this is the decision boundary. So there is also, so this classification is also not quite good. There's many random points scattered around. And for the leave one out cross validation approach, the parameter used is Laplace smoothing is equal to 0, and kernel density estimation and adjust is equal to 1. So the accuracy is about 51%. And this is the decision boundary, and it is also quite weird in the shape compared to the train test bed. So in conclusion, we conclude that the behavior class is separable. The genotype and treatment may require more careful labeling of the data because there are no obvious features are derivable yet. So for genotype and treatment could be the main reason why the class is hard to be categorized, which is the three combined class. So the naive-based classifier for behavior class achieve approximately 100% accuracy, and the naive-based agrees with the above results, which both genotype and treatment are difficult to predict. So in the previous result, we can see that the test train bed with 0.75 ratio approach obtained slightly higher accuracy than leave one out cross validation approach. This is because there is no randomness. There's a randomness in splitting the data set into the test and training set. So sometimes it can give higher accuracy, while sometimes it can give low accuracy. So it depends on the seed you set when you run the code. So for the leave one out cross validation, there will be all observations are considered. So there will be less bias and variability, and it reduces the overfitting problem. So most likely we will choose the result of the leave one out cross validation approach. Then that's all for my presentation. Thank you.
Okay, thank you for your presentation. I'm just curious, can we look at your leave one out models? So, okay, basically leave one train, okay, in doing this is the kind of, Okay, you're doing cross. Okay, this is just basically cross validation.
Yeah.
Out.
Using
that is a specific instance of a testing.
Using a specific parameter, which is this.
But what are these parameters? Tuning.
The FL is the Laplace smoothing.
What does it control?
Or it's sometimes because naive Bayes doesn't work well if the data is having like 1, 0 or high variance, right? So this Laplace will do the smoothing to the data set before fitting it to the classifier.
Yeah, so that the probability will not become 0.
It's not. So, it's not the parameter of the model. It's like the transformation to be done before fitting it.
Okay. So it just basically avoids situations where you may actually have a probability of being 0, right?
Yeah.
But it was not apply also. The model tells us to not apply based on the cross validation metrics. It chooses the model that don't apply this.
If you didn't, so what is the default value?
Default is 0.
Default is 0.
0 means there is no Laplace smoothing applied.
There is no what?
There is no there is no transformation done.
Yeah,
we just use the raw data.
Okay, because I think you don't need, right?
Yeah, don't need.
And the metrics itself also tell us don't need.
Then okay, let's look at the next one. Treatment. Okay, if the result is poor on 2 dimensions, why not you use small dimensions? Because you don't always have to use 2 dimensions, right? If 2 dimensions, okay, maybe it doesn't work on 2 dimensions. So did you try on more dimensions?
Because in the previous result, right, the PCA, like the t-test value shows that the only one variable is significant. So we choose 2, then it shows not significant. Then for the other variables, it should be also not significant.
Okay. I'm just curious about how is the decision boundary of the leave one out cross validation obtained?
Based on this model.
Is it because of we are not sure, but I think it's because of the use kernel. There's another function applied. I mean, can go back to the previous slide. Previous slide is using the same. So next slide, maybe they project it into another, don't know what space already here.
So okay, use kernel equals to true. What kernel function is used?
It states that is the kernel density estimation.
Kernel density estimator. Okay.
If false is the normal density estimation.
Okay. Do you know what that means?
I'm not quite sure actually.
Do you know how the kernel density estimation is applied?
Nope.
I think I explained it before, if not mistaken. Did I?
Yeah.
Yeah.
I mean, in this context, maybe don't know how to link it.
No, actually, I think I'm just curious how it actually draws the. because you leave one out, so you will have many predictors, right?
I think maybe it use all the observations, so maybe the shape will be quite weird.
Your kernel, okay, so basically when you do something like this, you have so if you have 2 dimensions, right? Let's say you have 2 dimensions, so you could actually have so let's say your okay, so your data points may be this is like a contour plot, right?
Yeah.
So this is for the black, let's say. Then the red one may be like this. Okay. So basically, what happens is that it basically estimates this. So the kernel density means that there's, you imagine that the 3 dimension, right? So there's one more axis like is facing you. The axis is coming from the computer screen and facing you. So there's like it's like a mountain, right? So basically, it will estimate that function. So that will be the function of x, y. So your x, y. So this one also has a function like g of x, y. Okay, so it will estimate this function. So this is your kernel density. So you have 2 kernel densities, right?
Yeah.
2 kernel densities. So it will allocate the label based on, it will find the argument max of your. So let's say you have a data point here, right? So you will find argument max of f, x, y, and g, x, y. So the argument is on which one? I mean, like if it is this one is larger, then it will assign let's say the red color, right? If it is this one is larger, then it will assign the black color. Okay. So this is what the kernel density actually means.
Okay.
So obviously, if you have a high dimensional space, basically this is just maybe x1, x2, and so on. So it can estimate some. It uses a non-parametric method to estimate this thing. After that, it's basically just they are just comparing at that position, right? They just compare the two densities, and they pick the group that has the higher one to allocate the label. So that's why you can see that their decision boundaries are very flexible. Usually naive base will have very flexible decision boundaries. That's why it will work very well in a lot of cases, because it's very flexible. Okay, so your conclusion is that only the behavior, okay, and it's predictable based on only 2 variables.
Yeah.
Okay. Okay, I think that the part is clear because you pick out the 2 variables and you show the. Okay. Okay, I think that's all. Thank you.
Okay, thank you.
Thank you.
Right, okay, so the next group for mice data.
Yeah, I'm ready. Can you share the screen first, Chang? Sure.
Yeah, wait a minute. I'm sharing my screen now. Okay. Can you see my screen?
Yes.
Yes.
Okay. Okay, let's start.
Good evening, everyone. Today I'll be presenting on the mice protein data set. Next slide, please. So this has 38 control mice and 34 trisomic mice. Each has 15 measurements. There are a total of 1,080 rows with 8 classes of mice. Next slide. So there are 3 variables, which is the genotype, treatment, and behavior. So in total, we have 8 classes binary for each of the variable mentioned earlier. Yeah. So next slide. So over here, these are the eight classes of mice that are being separated by the genotype, behavior, and the treatment. So next slide. From the data pre-processing work we have done is we have just dropped 3 missing observations because there are a lot of missing values. Then the remaining missing values, we have replaced them using the linear regression method as well as the median values. In deciding the 77 protein variables of the importance of their predictors, we have used the ANOVA. And our null hypothesis is that the mean are the same for all classes, and the alternative hypothesis is that at least one of the mean is different. So we compare each of the protein variables using their F values, and we shortlisted the proteins with high F values. We then use the principal component analysis method on the selected variables to determine the to have an observation of the underlying pattern of the observations. It was also used to shortlist the important variables that we will use for our SVM method. So next slide. So SVM is a supervised classification method. It is it changes the observations into a higher dimension using a kernel function. And yeah, we have actually separated the data set into the training and data set by 70 to 30% ratio. Next slide. Yeah, our model performance metrics, we have actually used three performance metrics to determine the stability of the model, which is the precision, recall, and accuracy. The precision is the proportion of true positive out of total positive. Recall is the proportion of true positive out of the actual number of positive, and accuracy is the accuracy. It's just the proportion of observations that is correctly predicted. My teammate will present the results.
Okay, next, we'll see the result of the analysis. So first, the result of the feature selection. First, we made a pairwise graph on the correlation, and we see that there's a lot of positive correlation between the variables. And before we drop the ones with the high positive or negative correlation values, we first perform the ANOVA test to identify the 30 proteins to see if there are any difference of means between the classes. We choose the proteins based on the F values. We first sort the F values, and then we choose the proteins, the top 30 proteins. We choose the top 30 proteins. And then for the principal component analysis, we perform PCA on those 30 proteins. And we see that from the PCA that the first 5 components covers around 95% of the cumulative proportion. And we graph those 5 components, but we hardly see any separations between the classes of mice. So we use other variables that makes up the classes of mice, which are treatment, genotype, and behavior. And we see that when we try to separate using these variables, we can see the separation between the behavior of the mice of PC1 and PC2. Yeah, as you can see through the scatter plot of PC1 and PC2, you can see clear separation between those two behavior. And then we see the top 10 proteins with the highest loading values. And these are the top 10 proteins. But from these 10 proteins, some of them are highly correlated as we carry out the Bayesian correlation test. So these 5 proteins are significantly correlated. So we only choose the one with the highest value of loading, which is PERK_N. Next. So as a result, we chose these 6 proteins to carry the SVM.
Next will be the result of our SVM model. So before we train the SVM model, we split our data into training and testing sets with a ratio of 7:3. And we use the 6 chosen proteins by the PCA to be our independent variables. And the response variable is class with 8 levels. And then we test our SVM with different kernels and different parameters such as cost, gamma, and etc. And we use the precision recall and accuracy to measure the model performance. So first of all, we train the SVM model using all the protein as the independent variables, and we can see that with the full model, most of the kernels, they perform quite well. And these are the results from the test set. And then later on, we train our SVM model using the 6 chosen proteins. And with the linear kernel, we can see that cost equal to 10 and 100 performs similar, and they are the top performance in the linear kernel. And then for the polynomial kernel, we use degree of 2 and 3, and the result of the polynomial with degree 3 performs the best. For the sigmoid kernel, we also choose gamma equal to 0.1 to be the best. And for the radial kernel, gamma equal to 1 perform the best among the three choices. So we can see that the SVM with 6 proteins, they perform quite well, but we are a bit hard to visualize their decision boundaries. So in order to visualize the decision boundaries, we feed a PCA with the 6 proteins, and then we pick the first and second principal components. These 2 components, they actually explain more than 86% of the total variations of the 6 proteins. Then we train the SVM models with the 2 principal components. So first we use the best setting of the SVM, which is the radial kernel, and then we can see that the decision boundaries, most of them look quite okay except for the green area. Although the precision recall and accuracy are not very good. And these are the decision boundaries for the polynomial kernel. Yeah. So even though for the visualization part, even though all the metrics, they are not as good as the original 6 variables, but it can somehow give us some idea about the decision boundaries of how the SVM doing. So as a conclusion, we have chosen 6 proteins, and then we have 2 SVM settings that perform the best, which is the radial kernel and polynomial kernel. And then we are able to reduce the number of independent variables from 77 to 6 without depleting too much of the model performance. So in this case, we can help to reduce the cost in data collection and data analysis. So I think that's all for our part.
Okay, yeah, thank you, Chia Chong. So your model, how many classes are there?
8 classes.
So you're predicting 8 classes?
Yeah.
Okay, I think this part we can kind of like ignore this part because the decision boundary is we don't always need to draw it. It's just nice that in case if you have very low dimensional representation, like two variables, then it's good to draw it. Otherwise, it's okay. So your test data. Do you have any result for your classification matrix?
Yeah, these are the classification metrics. They are based on the test set.
No, I mean the table for your prediction and the.
Oh, the table, no.
The one will be well, but that one is a bit larger, 8 by 8. Okay. How big is the test set? The total?
So for the training set, there are more than 700. For the testing sets, just 300.
Are there so many mice?
Yeah.
There's a total of 1,080 observation for 72 mice, I think.
A total of.
Actually, there are 72 mice, and each mice there are 15 measurements.
Okay, okay. So
yeah.
You are basically predicting the
Yeah, because based on the source of the description in the data source, it says that each measurements of the mouse can be treated as independent examples. So we didn't collapse the data.
Because okay, in some sense the data they still come from the same individual, right?
Yeah.
So they are not they cannot be independent in the strict sense. Like if you take measurements from your own body like throughout a period of time, right? Then you can't treat them as independent, I guess. Because otherwise, you know what? Otherwise, you could actually have a sort of like a funny situation like this. If you just do an experiment with one control mice and one trisomic mice, right? You're actually using two mice, okay? But then let's say you take 100 measurements per mouse, right? Then you will have 200 measurements, and then it seems like then you do your machine learning on that 200 measurements and you get something, but ultimately you basically only have two mice. So yeah, that's a little bit like what we call a pseudo replication. It's not a real replicate in some sense because the measurements are taken from one mouse. Okay. So I was wondering what your result was. It's actually quite different from the result of the other group. Okay, never mind. What happened to the proteins that you found? The features? Okay. How about the other group? Are any of these two found?
Yeah, for the behavior, we choose the CANAN and the SOD1.
CANAN and SOD1. Okay.
Yeah, for the
so
behavior.
that was found, but they have a few more other things. Okay.
But that is only for behavior only.
Behavior. You know, let me think about this. In spite of what they have done, now you know the data set, right? Is actually you don't actually have. If you talk about the mice, right, you don't actually have a lot, isn't it?
Yeah.
There are only 70 something, right? And then they are randomly allocated to 8 groups. So per group is actually very small already, isn't it?
Just around 10 to 12.
Okay. Now you have 15 measurements per mouse, right?
Yes.
Okay. So in fact, we might be able to treat that as in the case of some it's like oversampling.
Yeah.
Like but it's a kind of like something better than your oversampling because you basically actually have a lot because you are actually getting data that's real rather than you synthetically. So I guess you could actually justify your work on, like you are saying that's actually based on some kind of you are treating it as an oversampling. In order for you to maybe okay, so you kind of like assume that this is like you can treat it as an oversampling, so that actually gives you more samples to work with. Then and then discuss the result in that context. It's something like you know, you saw the previous few cases where they have very few unbalanced cases, so they needed to oversample certain minority class, right?
Yeah.
I guess you could view your study like this. It should be okay. Like it's a kind of oversampling. In that sense, your work will be like methodologically it will be coherent.
Yeah.
Okay. Okay.
Okay.
Okay.
That's interesting. Okay. Thank you.
Thanks.
Thank you.
So, and then the next group is on the glass data.
Yes.
Okay, go ahead.
Yeah. All right. Let's do this.
Can you see my screen? Hello?
Yes, yes.
Okay. Okay, well, we were given the glass data set, and I am Alex Enel, and my group members are Lee Chia Hung and Si Kim Ting. So today we're going to focus more on the decision tree using guide and card. Before moving forward, I would like to recap a bit on the glass identification data set. This study is actually about the classification of types of glass in criminological investigation. At the scene of the crime, the glass left can be used as evidence. It can be, if it can be correctly identified. So there are actually 214 samples, the data set with 6 types of glass and 9 variables, which is shown below. And next. So we are actually going to perform classification based on this data set, and it is a multi-class data set. So before training a model, it is better for us to split into a train test data set, where we can use this test set to judge whether a model is overfit or not. So this glass data set is split into 75% train set, includes 162 rows, and 25% test set, 52 rows, which is 75 to 25. We actually wanted to check whether we can go for like 80-20 or 70-30, but because our data set is too small, 80-20 will result in a test set which is very small. And what about 70-30? 70-30 also will result in a too small validation set, which will affect in the performing of cross validation. So then based on the graph, you can see on the left is the train set, and on the right is the test set. So what we can see here is type 1 and 2 type glass 1 and 2 is the highest in number. And compared to the type class 6, which is the least, we can see that this is an imbalanced data set which might cause an issue when fitting the model. So, but let's interpret the preliminary result of model first before we move forward to the modeling. As I mentioned before, we are going to use two different packages to fit this decision tree, which are the guide and card tree. So first, a guide and card tree is fitted with default settings, and the accuracy for the respective guide and card tree is shown below for the train set accuracy and test set accuracy. And it seems that our card retain high accuracy in both train and test set. So for further explanation on this guide and card tree, I would like to pass to my group member, Sikim. Thank you.
Okay, so I will present more details about the difference and comparison between card in R or just R part and the guide, and see how they grow the tree and the comparison of their performance. So first, we look through how guide grow the tree. So this is a tree structure for the training set, 162 rows, and we go most of the settings by default, except that because of the cross-validation problem that mentioned by Alex just now, we set from 10 to 5 for cross-validation because of the relatively small train set. And the rest, like the rest of the setting, like maximum depth and also the minimum split, there is the minimum observation in the node, are all go by default. They are set by the guide program. And from the tree structure, if for the node, right, if the condition is true, it will go to the left, and if it's not true, it will go to the right for further decision node and decision splitting. And there's one thing to note from this tree structure generated by guide is that we may see there is the node number 8 is actually a linear split. That means it's not by a univariate predictor. It used two bivariate predictor. There's magnesium and calcium. So guide will automatically use linear split whenever it thinks it needs to. And also one thing to note from this tree structure is that we cannot, how to read this, actually to read the tree structure, right? The number beside the node is the mixed classification number, and the number below the node is the class type. That is our class label. And the second row is actually the sample size in that node. So from here, we can see there is no way that any data will be predicted later into class type tree. As we see from the leaf nodes, there is no class type tree. Yeah, there's one problem, and we will further discuss this problem later. And also for the variables they use in building this tree are barium, aluminum, calcium, silicon, magnesium, and potassium. Okay, next. Next slide. Okay, so just now was the tree grown by guide program by default, and now we shall see how the card in R or R part grow the tree. And also we set to 5 for cross validation, and the rest we also let R run the model building by default. Also the maximum depth is set to 30 and the minimum split set to 20. And from the reading of the interpretation of the tree structure is similar to guide. There is before the slash is actually the right side, the left side of the slash is the correct prediction, and the right side of the after the slash is actually the sample size. So we may see also start from barium, and yeah, also the similar variables are used in the splitting. And also one thing to note is that there are some problems with this the card tree also, because the class type number 3 and number 6 will not be predicted in this grown tree. And also in the middle and the bottom part, we may see there is repeated use of refractive index. The middle bottom part, repeated use of refracting index to classify class 1 and 2. So this may be a problem which we shall discuss later also. So next. Yeah, so we see how the difference between the tree grown by guide and card, and now we see the multi-class confusion matrices for the text set, which are 52 sample size. So we have mentioned by Alex that generally card are more accurate. The accuracy for card is actually higher, and yeah, we shall explain why later. So next slide. And there are some summary of the comparison. First, guide and card by default, without tuning any parameters or setting any parameters, guide and card will produce almost the same tree with the similar level of complexity. They have the same size. There's a number of nodes are both equals to 15, and the depth of the tree are 6, and the number of leaf nodes are also the same. There's 8. But there are some difference, which guide for training, they will not classify any data into the guide type tree. But for card, apart from guide class type tree, also with guide type 6, card will not classify any data into these two types. And for the testing and the performance, or the performance of these two trees, guide have lower accuracy, also low average sensitivity. Here we use the average because each class got its own sensitivity, so we just calculate and average out. And also lower average specificity compared to card tree. So it looks like, but for the sensitivity is actually because of, we can see there's balanced sensitivity for most classes for guide, because like it can predict, at least can predict number 6, but for card, it cannot predict class number 3 and number 6. So it looks like generally card perform better, but there is some problem there. Okay, next. So some of our possible explanation of why it's happening is that the high accuracy and average sensitivity of card tree might just be a false appearance. That means it may be just an illusion, because this is because the high accuracy and average sensitivity was driven by the correct prediction of class type 1 and 2, which are very high in proportion in our text set, like 4 times compared to the rest of the classes. And also we noticed that there is a deep splitting among the class type M2 recursively using the same refractive index feature. So by default, guide used bivariate predictor sometimes, and there's linear split to classify type 1 and 2, while card repeatedly used univariate predictor, there is RI. So this might be an indication of possible overfitting to specific attribute of the sample data. And also, tree built from card is only sensitive to classes with higher frequencies. There is type 1 and 2 with very high sensitivity, but 0 sensitivity to class type 3 and 6. And despite lower performance of this data set, we think that guide should have overall more stable predictions and generalization for new unseen data that is apart from this particular text set. So for further discussion, I will pass to Chiao Hung.
Okay, thank you, Sikim. So next, we'll talk about how do we improve the model result. So there are multiple ways that we can do it. First, we can either tune the hyperparameters and others. So among the hyperparameters, there are like the minimum split or the maximum depth. That for this presentation, we are not tuning them. We just showcase the first very simple case of like changing the estimated, changing the prior. So there are like, can use estimated prior or uniform prior before you start to fit any data. Card by default will use estimated prior, and guide by default we also use estimated prior. But apparently after we change the prior to uniform, guide perform better. And but however cut is is performance reduced when it's changed to uniform prior. In this case, guide with uniform prior has a better accuracy. We talk about accuracy here is that the test set accuracy. We normally don't really look at train set because train set accuracy might be prone to overfitting. We have to look at the test set accuracy. So in this table, guide with uniform prior has the highest test set accuracy. So next, this is a feature importance that is produced by the two models. Apparently, they use different criteria and different methods in coming out with this feature importance. As CART generally, it measures the variable, it measures the sum of goodness of split measures for each split. But guide, it will use the chi-squared statistic computed during variable selection to calculate the importance. And you can see that in both chart, barium is the most important variable in the decision tree. So this chart, normally how we interpret it is that if the variable importance here, there is the big difference between the most important and the least important one, right? Those that is like least important that we can actually drop them from the model so that to reduce the complexity and improve the computational time. But in this case, our variables only have like how many variables? Only have a few variables. So and then the variable importance come up. The result is like they are almost equally important. Like there's no big gap. So they will not do anything on this. So next slide. Okay. So besides tuning the hyperparameter or setting the prior or whatever, we can also use another method, which is the ensemble method, because it's believed that a combination of multiple speed learners can result in a strong learner that can make a wiser decision and better prediction without overfitting the data. As here we present random forest. Random forest is one of the bagging methods. So-called bagging methods means that you build a lot of big learners and then you put them in a bag and then you vote by the majority vote. In this case, actually bagging, you can actually not only put trees inside the bag, you can also put a lot of others kind of like linear regression or SVM into the bag, but we are going to put all trees inside the bag so it becomes random forest. So each tree will be exposed to different number of columns and different rows for the randomity, like, because it's called random, right? So here we also use the default, which is 1,000 trees. Okay, so there's 1,000 trees here, and then they will vote which one, and then we'll look at the accuracy. The random forest package current used here is not the CART, but is just another random forest package from R. We just want to use it to compare with the guide random forest result here. Okay, so we can see that guide random forest generally give a highest test accuracy. Next. Okay, from this confusion matrix for the test set, right, it differs from the single tree, as we can see that there are a classification into glass type 3, glass type 6, glass type 5 that we are missing in the single tree, so that you see they are like they can be predicted in this way as compared to the single tree. So for random forest, the performance is better, the accuracy is better, and then they are like every class get predicted. At least they get predicted. Okay, next. So this is the feature importance that is produced by the random forest package in R. But then it just means that for each glass type, which variable is important in like splitting out and then to classify that certain glass type. You can, for instance, for glass type 7, you can see that barium is very important, as barium can like single-handedly predict well for glass type 7. This is what the random forest has given. There are also methods of how random forests score this kind of variable importance that you can look up online and read on the paper. So this random forest by R, they actually implement the Bryman's algorithm. Okay, next. So lastly, future work is that because our sample size the first one, if you talk about imbalanced class data set, we might want to consider to resample it to make it like more uniformly distributed, or we can collect more data as class, the data set is really a bit small for 200 rows with 6 classes. We might want to collect more data, and then we will perform more hyperparameter tuning on the trees of a random forest, or the cross validation, or the like mean split, or the max depth. Okay, next. So thank you.
Okay, thank you, Xiao Hong. Okay, yeah, it looks like an interesting analysis. If you go back to the early slides where you first showed some results that cut seems to be better. Yeah, okay. And then after that, you made some, yeah, as you said, the train set accuracy, usually we are not so, we don't take it extremely seriously because it's usually, we have to look at the test set, right? Because the training set, usually it will do well, right? So you have to got to look at the test set. So don't get very happy when your train set has very high accuracy, right? The real thing is in the test set. Because usually if you increase your model complexity, your train set accuracy will increase. But it may not actually generalize to the test set, right? And then I think you made a good analysis about the differences. Okay, you move on. Right, where you actually showed, yeah, this part, right? So here, although you look at the testing performance, a lot of the metrics are lower for guide, right? Now, someone who doesn't really understand the issues, right, will immediately go and pick guide. Sorry, pick cut, because the metrics are all higher, right? So this example shows you that you actually need to go beyond just comparing metrics, right? You have to really think about the algorithm, and also notice important things. I think you notice very important things here, where cut, you see that it's not classifying any data into class type 3 and 6. So it's already biased. It's actually known already that cut is biased against the class with the small sample size. Okay, it's biased towards the majority class. So this is actually it's actually the person who created guide actually knew about it. So here is actually demonstrating that, right? So you see that although guide is doing on this data set, doing the performance is actually lower, but it can actually predict type 6. Okay, so you think about it like this: if you give it a test data, right, where everything is type 6, which one do you think will win? Right, let's say I give it a test data, right? All the test data are type 6. Which one will do best?
Guide, because cut will give you all wrong.
Sure.
Zero accuracy.
Yeah, because it's biased, right? Because it cannot detect it, in the training. It's already affected by the fact that you are using. It's very sensitive to the class imbalance. Okay, whereas guide is actually less sensitive, right? So yeah, that's why you have to think of it like this. Yeah, you cannot just look at metrics and then draw firm conclusions, right? So I think you made this quite clear, right? Then the next slide, okay, I think this discussion was actually very well done, right? Where you actually notice that they repeatedly splitted on the same variable multiple times. Okay, so they are actually kind of like overdoing certain things. Okay, the same variable, use it to split multiple times. So that's actually an indication that there's some kind of bias. The tree is actually going in some kind of bias direction already. Okay, so you pointed that out, right? Okay, so yeah, so this part is actually very very thoughtfully done, I would say. Yeah, there's a lot of thought that went into it. Okay. And then how about random forest? The result from random forest is actually, yeah, this one also, the use of the prior is also important. Yeah. Generally, I would suggest that we just keep it to the uniform prior. If you use estimated prior, I don't know. Unless you have this prior is some kind of a penalty for certain classes, right? So if you don't have a clear idea what to do here, I would suggest that you just go with the uniform prior, because if you go by the estimated prior, it may actually wrongly penalize the minority class, because some classes, right, they might be minority in reality, but in your training set, right, it may not be the minority, you know. Okay, the majority becomes the minority simply because of sampling issues, right? So if you go by the estimated prior, it's a bit dangerous unless you really have random sampling. But most of the time when you deal with data mining, you cannot assume your data is randomly obtained, because it's most probably observational, and that's why it may be just safer to go by uniform prior, which basically says that, well, you are basically just treating every class as the same, right? And this seems to give better results, right, for guide. Okay, and then your test accuracy is 67.3. So when you do random forest, it pushes up about 4%, is it? Can you show the result on the random forest? Yeah, it goes up by about 4%. Yeah, this is usually I think the usual observation is that when people, after you have done a classification tree, if you go ahead and do a random forest, it usually will boost it around 4 or 5% in terms of the accuracy. This is actually quite widely reported. Many people's experience. The boosting will add about 4 to 5% of. It will squeeze out a little bit of these extra results, right? But it will also depend on what is already your accuracy. If your accuracy is actually not very high, you do random forest, it will squeeze more. But if it's already very high, let's say your test accuracy is already like 90%, you go and apply random forest, you may only squeeze out like 2%, right? So how much you get is also dependent on your test data, the test set accuracy with the full data, with the full tree. But generally, you can expect some improvement with random forest. Okay. All right. Okay. Thanks, Chao. Thanks to your group for the presentation.
Thanks, Kim. Thanks.
Thanks, Doctor.
Okay, thank you. The last group. Let's have the last group.
Yeah, good evening, everyone. Can you guys see my screen?
Yes.
Okay, thank you.
Hello, doctor. Can you hear me?
Yes, we can.
Okay. Now let's start my presentation. Hello, everyone. Good evening. I'm Amy. This is our group assignment 2 presentation. Support a vector machine on class dataset. Next. The contents of my presentation include the 4 parts: introduction, methodology, result, and conclusion. Next, the first part is introduction. In this project, we used the GLASS dataset, which is from the UCI repository of machine learning databases. The project is to predict the type of glass on basis
of its criminal analysis. We used the GLASS dataset in this project, which contains 214 instances, and it includes 9 independent variables and 1 dependent variables. And the table 1 shows the attribute information about GLASS dataset. And the next slide shows the figure, the distribution of the type of glasses. And the distribution of each type of glass is different. Our dataset is unbalanced. On the right, each number corresponds to a different type of glass. For example, the number 1 means building window float possessed. Next, the next part is methodology. Next, the slipped train test. Train test slipped procedure is used to estimate the performance of model when they are used to make predictions on data which are not used to train the model. Datasets are split into training and testing sets according to 7:3 ratio based on the distribution or proportion of the class. As we show in the right figure, 30% of each group, which represented by dark yellow, randomly selected as testing set, and 30% of each group, which are represented as light yellow, are randomly selected as training set. Next. Support vector machine, a supervised machine learning model which use analyze data for classification and regression analysis, performs well on limited amounts of data. Objective is to find hairplan in an n-dimensional space, which distinctly classifies the data points. Data points falling on either side of hyperplane can be classified as different classes. Specifically, C classification support vector machine is used in this study. Kernels such as linear, polynomial, radial, and sigmoid are used to find the best model. For each kernels, different parameters such as cost, degree, and gamma are tuned. Next, we will evaluate the model based on the 3 indicators. The first indicator is precision, major factor of relevant instance among retrieved instance. The volume precision equals to TP over TP plus FP. And the second indicator is recall, major factor of retrieved relevant instance among all relevant instances. So volume recall equals to TP over TP plus Fn. The last indicator is accuracy, major proportion of true positives and true negatives. The volume accuracy equals to TP plus Tn over TP plus Tn plus Fp plus Fn. Okay, BW will continue.
Next slide. This is the result of the ANOVA test. We did it in the assignment 1 last time. It's just a recall on the top 7 significant variables, which we have selected based on the ANOVA text. Next. We first performed the support vector machine model with all variables. We have trained different SVM model with different kernels and parameter. Next. In these linear kernels, we use 5 different parameters to find the best model. Unfortunately, we found that all the models have the 0 precision in this kernel. This may be due to the smaller testing sets. Next. In these polynomial kernels, we found that all the models also have the zero precision in this kernel. Next. In the sigmoid kernels, all the results are not performing good. Next. In the radial kernels, model with parameter cos equal to 10, gamma equal to 10 have the same performance with the cos equal to 100, gamma equal to 10. Since both results are the same, we choose the model with the lower cos, which is the cos equal to 10. At the same time, this model have the best performance among all the models we have trained in the different kernel. Next. We analyze the best one in detail. This is the confusion metric of the best model. The diagonals is marked in blue to indicate the number of the correct predictions. I take the type 1 as the example. There are 21 type 1. 18 are correctly predicted. 2 are wrongly predicted as the type 2. And 1 is wrongly predicted as the type 3. And then my group member will continue.
Yeah, as Biwa has mentioned just now, we have selected the top 7 significant variables in our previous assignment. Hence, we run through all the training process on these selected 7 variables. In linear kernel, the performance of all the models with different parameters are not good, as the precisions are all 0. This is the same as for the kernel polynomial. The sigmoid kernel, the models are all badly performed. However, in radial kernel, one of the model that can be considered as good, which is a cos equals to 100 and gamma equals to 10. It has a precision of 70% and recall with 62%. The overall accuracy for this model is 68%. So this is the best models trained on the top 7 significance variables. This confusion matrix shows is a model trained on the top 7 significant variables. As we can see, the diagonals is the correctly predictions. So comparisons have been made between different SVM models with different number of features and different combinations of parameters. The best model trains on all variables is the radial kernel with parameters cos equal to 10 and gamma equals to 10. Whereas the best model trained on only the top 7 variables is the radial kernel with parameters cos equals to 100 and gamma equals to 10. So based on the comparisons, we select the models which trains on all the variables in terms of the precisions, recall, and accuracy. Yeah, that's all from our group. Thank you.
Okay, thank you, Kyung-hwa and the others. So can I look at the difference between the 2 models? So your accuracy is 68%.
This is the model which trains on only 7 variables.
The other one?
This one is the one trained on all the variables.
Okay. So, and then your conclusion is that the one trained on all variables is better?
Yes.
And what's your justification for saying that?
Because since we have a less number of, the size of the data set is quite small, and our training and the testing set is also quite small.
Okay. So your
And so if the model that the model that trains on all the variables, it has a higher accuracy.
But your test data is actually quite small, right? And
yeah.
Of course, in this case, you only did it for one instance. If you randomize it for many instances, then there will be some kind of a distribution of the accuracy, right?
We split our training and testing set according to each group of the class.
Yeah, sure. But there's only one instance of splitting, right? You can basically repeat this for many times, right?
Yes, yes.
Okay, but I know, but it's not necessary to do that in this in this course. But because I'm saying this because your difference is actually quite close, you know, your accuracy.
Yeah.
Between the two models is actually quite close. Although one is actually like 0.03 more, but you have to remember that this difference is based on an examination or one particular randomization of your test sample. If you had done it like, let's say 1,000 times, you would have a distribution of the accuracy values, right? And then these two distributions may overlap substantially, so suggesting that they are on average, their accuracy, the mean accuracy does not differ that much between them. So because you are looking at one instance here, so it may not be, I think a better way to say may be that they are more or less the same, you know, on the basis of just examining one sample. And besides, in fact, if you can measure 7 variables compared to 9 variables, measuring 7 variables is definitely cheaper than 9 variables, right?
Yeah.
So, but then again, it may not make a difference. It may actually depend on, because the variables may be kind of like generated as some kind of a package. Like, you know, some chemical analysis, they go by a package, right? So, I just give you this, I just measure these variables for you for a certain price. So if you want to customize it, in fact, it may actually become more expensive.
Yep.
So, okay, I think also the other difference is that whereas in the guide result, right, I think the model had problems predicting class 3, right, for both guide and card. But in your case, you don't have this problem.
Yeah, but yeah, since the testing data set is very small, so only very less predictions is correct.
Okay, but at least it could predict. It could actually predict class 3.
Like for this class 3, there are total 5 numbers of instance in this type 3, but then only 1 is correctly identified.
Yeah, but at least it predicted 4, right? You go by the row, it predicted 4 as type 3. So whereas in guide and card, they predicted nothing.
Yes.
They couldn't predict 3. Card was even worse. It couldn't predict 6. But they could solve that problem by doing a random forest. Whereas in this case, you don't have this problem with SVM.
Yeah.
Okay. Okay, thank you for your presentation. All right. So I think the idea is to see how different models actually behave even with the same data set, right? So all of you will have some idea about how to use this kind of methods, right? Like for example, if you use SVM, as you have seen your friends work on SVM, you have to consider different kernels and also consider the parameters, right? So it's actually quite a lot of work. Although you say that you want to do SVM, but actually you have to pick the correct kernel in that method. And even after picking the correct kernel, you have to tune the parameters, right? So it's not just you know, simply selecting one kernel, one particular parameterization, and then just report the result, right? Because there are many possibilities. Okay, so I hope you have seen that from everyone's presentation and take a note of that. And also you have also actually looked at how to use guide, right, as a tree method to understand that it is sometimes possible that it may fail to predict certain classes, right? So, and you may have to adjust for that deficiency with a random forest, okay? It's always a bad idea when your tree cannot predict one of the class. If you have, usually this happens in a multiple class problem. If your tree cannot predict one of the classes, then you have to start to worry already, because that means in practice, when I give the test data from that class you fail to predict, your model will crash completely, right? So that's very dangerous, okay? So if you find that consistently certain classes cannot be represented in your tree model, then maybe the tree model is not a suitable model for your data, okay? And then what else have we looked at? We also look at ANN. So you have to be aware of the nature of ANN as a black box. Okay, you will struggle to use ANN to explain your variables, all right? But it will. But the plus side is that it is probably very good in if you know how to tune it. And then if prediction is only something that you, in your project, is something that you care about, right? Explanation is not important, then go ahead with ANN, right? But you do realize that there is it's kind of like known as a downside, as a black box, okay? And then naive Bayes, right? Naive Bayes is actually recommended as one of the frontline classifiers that you should always try, okay, because of its flexibility, okay. The naive Bayes is actually surprisingly flexible, but again, naive Bayes may be, the problem may be that it's not clear which variable is important in the prediction, because it is a probabilistic method, right? It's taking all the probabilities into consideration, right? Probabilities from different features. So in some sense, it may also be much closer to the black box kind of situation. So if you find that, but then again, black box models are good for prediction, right? Not good for explanation. So you may find that if you only need to do prediction, then naive Bayes is something that you should also consider, right? In addition to neural network. Okay, that's why naive Bayes is commonly used in text machine learning concerning text data. Okay, because in text data, basically you don't really care about the explanation. You just want to classify certain documents as belonging to whatever class based on the usage of certain terms, right? And the terms that you consider are a lot. So basically, then if you just want to classify like large scale classification of, let's say, articles, right? Whether it is a science article, economics article, culture article, right? Without actually reading it, then naive Bayes would be the method of choice, right? Okay, so I think generally those are the models that we covered. So, okay, so I hope you enjoyed working with the project. I mean, like, this is something like a full cycle, but it's still not complete because, but then it's okay, right? This is just an introduction course. So you have some experience taking the data from the raw form, doing some necessary processing, right? Maybe even transformation, dealing with missing data. And then after that, do exploratory data analysis, right? To see whether there are certain patterns in your data. And so doing feature selection, if that helps. And then finally deploying the model. And also you can see that when you deploy the models, there are many possibilities. So you can pick certain candidates, right? And also how do you go about doing the evaluation, right, of the models, and also how to think about the results. Okay. So yeah, so I hope this will give you some head start on working with this kind of problems. It's actually not that hard now that you actually have come across it as a full cycle kind of approach. Okay. All right. So for this part, you will the group representative will submit the slides to Spectrum. All right, and then the individual reports you will submit on Saturday. Okay, so you can actually use the feedback that you receive in this session to help with your individual reports. Okay, so the details about the evaluation of your reports are in Spectrum. So I hope you have seen the announcement.
Yep.
Okay, so don't write too many pages. So I just keep to the number of pages so that you just focus on the important things, right? Just you need to decide what to go inside the report and what doesn't need to go into the report. And I forgot to say about the font size. Just keep to font 12, yeah? Keep the font 12, use, you can use the spacing, you use 1.1, I think you use 1.5 spacing. That should be okay. Because otherwise, if I don't say the font size, right, and the spacing, right, some students will try to...
I will squeeze it.
Because it's a loophole, right? Oh, you didn't specify the font, you didn't specify the spacing, I just squeeze. Right, so I just... you keep to font size 12 and then spacing 1.5. I didn't write it down there. So you take note of that, and you don't have to have the first page. You just need to put your name, your matriculation number, and then start writing. Right, you name, matriculation number, and the cost. Right, that's all. If you work on for the group, right? So you just mention which group were you on, okay? With who are the group members? That's all. Then you can start to write your report, okay? You don't need to have like a fancy cover page and whatever. Don't need that. Okay, I'll just read your content.
Would like to ask about actually what is the materials that stated in there.
Materials is your data set.
Oh, okay. Okay.
Your materials is your data set. Your methods will be how you dealt with the data set, the data pre-processing, and the modeling. Okay, and how did you do the evaluation? Right, those things all go to methods. Okay. Okay, so I think that's about today's presentation. Then just a quick note. I actually have I actually owe you one session of the lecture. That one I need to make a video, but I'm still trying to find some time to make the video. So I'll post it up sometime this week. It's basically just saying something about the bias and variance in the models, right, and how that relates to the model complexities. So just so that you have some idea about the trade-off. There's a trade-off between bias and variance. So you will not have a perfect model, because a model that is highly biased will have low variance, and vice versa. So if it has low variance, then it will low bias, they will have high variance. So the idea is to find some kind of balance, okay, that so that your model has the best hope of generalizing future unseen data. Okay, so the two extremities, you have to kind of like avoid those two extremities, right? So it's just a short video on that topic. Okay. Other than that, then is the exam. So the exam is 24. It's a take-home exam, right? 24 hours. So was the date already announced to you?
Yeah, it will be on
supposed to
6
be on
or
a
7,
Friday.
I think.
It's on a Friday, I think. Supposed to be on a Friday and ends on a Saturday.
Yes, it's a Friday, but yeah, I forget the exact date here. Let me check.
It's the 5th, right? 5th of February, right? Okay.
Yeah.
Did everyone receive that from the coordinator or someone or somewhere? That information.
I think you put it in Spectrum, and also yes, we did. It
I
received
already.
some.
I mean, officially, did you receive anything? Officially,
I think it's in the website, right? The Institute of Malaya website. I mean the ISM website.
Yeah, the SMS site they have it. Yes.
So it's already published there, lah.
Yes.
Okay.
Yes.
Okay, so then fine. So it's 24 hours. So I will put up the paper at 10 o'clock in the morning. Okay, on Friday. Or is it like, how do you want it to be done? I mean, like some of you are working, right? So because it's 24 hours, so if I put it on Friday at 6 o'clock in the evening, then you can submit 24 hours, so that'll be 6 o'clock evening Saturday. So how do you want it to be done?
Evening.
Wait.
Yeah, evening.
Evening.
Okay.
I cannot miss a day because I have some kind of presentation also in the morning. So evening.
Put like evening, like what time? Like
6,
6, 9?
6.
The later the better, right?
I just ask you because I can put any time. So what do you all want? Well, I mean, this is more for the people who are working, because
then you create a poll, then people will vote. You buy you one.
People here, you want 6 o'clock, 9 o'clock?
I'm fine with both.
Prefers 11 o'clock. 11 o'clock, people are already sleeping.
Yeah, it's maybe I'm okay with anything lah. I mean, I don't have really preference. It's only until the next day, 24 hours. How about Saturday to Sunday? I like your suggestion.
It's already fixed, so it's already fixed. So I can't change that on the, because it's already published already, so I can't change it. How about others? Put it at 10 lah. How about 10? 10 to 10 lah.
I'm okay with it. Yeah.
PM, right? 10 p.m.
Oh yeah, it's PM, right?
10 p.m.
If 10 a.m. I die.
10 p.m. So you go 24 hours, then you will, it's what?
10 p.m. the next day.
The next day, 10 p.m. That should be okay. Enough time, right?
Yeah, got time to sleep, right? At least.
Wake up earlier. Wake up earlier and do it.
Yeah.
I actually read the paper first and get some ideas, then wake up early to do it.
Yep.
Or maybe after you see the paper, you cannot sleep.
High chance.
That's high chance, but yes.
My God.
Depending on the difficulty itself, right?
It won't. It's I consider it standard. I mean, like it's just standard. But you do have to. Yeah, you will use all the methods that you have learned. It doesn't have things that I didn't teach. Okay, so I mean, like just now you did some in some of the projects had problems of unbalanced ratio, right? So they needed to have some special methods to do that. So that's not covered in the class, right? But then those things are not very difficult, so they kind of like learn extra. So I don't have those things in the exam, right? Exams are purely things that I have talked about, right? They are in some form of notes. Okay, so or maybe mentioned before in the video. So you can. Right, so it's also open book. Okay, you can consult any sources. You just can't talk to each other. That's all. All right. Then the R code, everything. You can use the recycle the whatever code that's been in Spectrum, or even if you want to find online codes, up to you. You want to write your own codes, up to you. Okay. So I don't really have as long as the code actually works, but of course you're not going to get like questions where you can just simply paste some code online and expect it to run, right? But you still need to understand the R code a little bit, and then maybe change some parameters, and then it will run, right? So you will be given that there will be one problem where you actually have to work on a data set, right? I will give you a data set, and you have to work on that problem, okay? That means you have to write some R codes and then do some calculations and explore the data. All right, and then after that, the questions are a bit more theoretical. Okay. I mean, theoretical, slightly theoretical, and maybe also just testing your understanding of certain concepts. All right, whether you know how to apply the concept appropriately.
When it comes to theoretical, it's not about like the formula itself.
I don't have like maths, all that to torture you, because there's no point, because if you ask those things, you cannot ask in this kind of situation. You can't really ask very theoretical things, because what happens is that either students will completely just copy something and dump it on me, which I don't want. Is completely pointless, right? Or you have to come up with something that is some kind of a further derivation or whatever based on some existing results, which I think, which I also don't want, because that will get very mathematical, and it doesn't really actually it's too niche into that kind of detail. So that's also not very helpful. By theoretical, I mean like you at least have to understand like the mechanics of certain methods lah. Okay. So basically things like that, right? Well, interpret, okay, based on certain principles, interpret certain results. Okay. So it won't be very it'll be something that is just above your level. Okay. So if you have been following the course and then doing some revision, I think that there will be no problem, right? Okay. Okay, so I think that's all for this course. All right. So yeah, so I hope you have enjoyed it.
Yes.
Yeah. Yeah.
The clapping hand on the, I think somewhere there's a symbol that you can clap.
Yeah. Oh.
I think.
But then the one don't come with sound effect.
Yeah. Do you see it?
Yeah.
Okay. Yeah. So I think that's all. All right. So thanks for getting this far. Yeah. Okay. So if anything else you want to ask, just you can just go to Flock and ask the question, or just put on Spectrum. Well, I think you'll just use Flock.
Okay. Sure.
Okay.
Okay, thank you.
Okay, good.
Yeah.
Thank you, Dr. Khan. See you next semester.
Okay. Well, I know Chao doesn't want to see me. You want to graduate?
No I so it's the distance between us. So. My God.
Okay.
Graduating soon already.
All right. Okay. So have a nice evening. Okay. Bye bye, everyone.
Okay.